This is the Guardian Controller project for EEE174 by EcoElectric. This is our block diagram showing our three different inputs going into our microcontroller and coming out with two output values and having that data from our inputs logged through UART to a Raspberry Pi. And in our FSM diagram, this is the general setup loop for our Moore state machine that we will go more through in each of the test cases going on here. The test cases are delegated to Albert, Lauren, and Scott, and we all collectively worked on the FSM diagram. So the first one is the RTC clock, which I did with the purpose of having the STM32 microprocessor go into a sleep or standby mode for a certain amount of time and waking up with an internal alarm, and then going through logging our data and getting all the inputs and outputs, and then going back to sleep for a certain amount of time, and so on. Then is the water valve, which based on the inputs of soil moisture sensor and a temperature sensor. It turns on a LED representing the amount of time the water valve would be open and outputting through one GPA output in the picture on the right being PA7.
I am in charge of the temperature sensor. This was one of the test cases that I was in charge with, and I modeled this with a TMP36 sensor. To model this on my breadboard, I use the equation below. The temperature in Celsius is 100 times the voltage in reading minus 50, and to convert this in Fahrenheit, I used the following equation that Fahrenheit is equal to 1.8 times the Celsius plus 32, and I use this from the data sheet that is below on the left in that graph, and as you see on the right, that is the reading in MobaX, and we can see the heat being displayed in Celsius. The next one that I was in charge of was the heat lamp, and to model this I used an LED. We wanted the heat lamp to turn on when the temperature was below a certain degrees, which was 21.5 degrees Celsius, and you can see that modeled below with the if-else statement in the code.
So for the soil moisture sensor, it's a pretty simple sensor that has two probes that is put into the soil, and it essentially measures the resistance between the two probes, and that can be related to soil in dry conditions, which I found to be about 75 ohms, or in wet conditions about 15 ohms. And using this relationship, we can establish a linear equation that relates the ohms to the voltage from the microcontroller, which my equation for that is in ohms equals volts times 18.2 plus 15, and this was used in the RC file to calculate the soil moisture. This is just a slide showing in the IDE the input for ADC2, and then on the right it shows the raw value, attaining it, and then multiplying it with voltage, and then getting that moisture value. So setting up in the IDE, we configured it to export serial data over the UART2, and that was configured, and then on the receiving side we can use Python to receive that serial data, just keeping in mind that we need to have similar port configuration and baud rate so that it speaks with the microcontroller properly. And then in Python we can write a script to import that serial data and then save it to a .csv file.
In conclusion, there are a few things we could have done differently, which includes including a failsafe on the water valve to prevent overwatering. We could have also tailored our water profile towards specific plants. For example, like a cactus, it would not need as much water as another plant. And we could have also used a more sophisticated sensor for capturing soil moisture. And if we had more time, we could have gotten all of our test cases to work, as well as when everything is compiled in our FSM, we could have tried to have receiving values for all test cases. And the ones that were successful in terms of test cases were the temperature, heat lamp, and soil moisture sensor. And the test cases that could have used a little bit more work was the RTC, since we could not get it to restart after shutting down, as well as the water valve because we could not get the LED to turn on when the temperature was too low. These are the references that we used to model all of our sensors, and this concludes our final project for EEE174. Thank you.